Every 75 years or so, a 15-kilometer-wide iceberg made of rock and frozen gas dives through the inner solar system at over 70 kilometers per second, and we can predict its arrival to the year, centuries in advance. That returning wanderer is Halley's Comet, the most famous of all. It's what astronomers call a short-period comet. Its orbit around the Sun takes about 75 to 76 years. The path is a stretched ellipse, like a rubber band pulled almost to breaking, reaching from well beyond Neptune's orbit down into the inner solar system. Each time it swings close to the Sun, sunlight heats its surface, frozen CO2 and water sublimate, turn straight from ice to gas, and jets of escaping vapor drag dust into space, creating a coma and tail. But this spectacle has a cost. Every pass erodes the nucleus, shaving off meters of material, so over millions of years, Halley will literally evaporate away. Humans have been recording Halley's appearances for at least 2,000 years. Medieval chroniclers saw it as an omen. Chinese astronomers carefully logged its position. But it was Edmund Halley in 1705 who noticed that bright comets in 1331, 16082 followed nearly identical orbits. Using Newton's law of gravitation, he proposed something bold. They were the same comet, returning under the Sun's gravity. When it came back in 1758, right on schedule, this was the first time a comet had been successfully predicted. Halley's insight turned comets from cosmic surprises into calculable members of the solar system. We've now visited several famous comets up close. In 1986, the Giotto spacecraft flew just 600 kilometers from Halley's nucleus and revealed something unexpected. It was black, darker than coal, because its surface is coated in complex carbon-rich material. In 2014, ESA's Rosetta mission orbited Comet 67P per second Churyumov-Gerasimenko for over 2 years, watching its activity rise and fall. Instruments detected organic molecules, including amino acid precursors, chemical building blocks of life. These missions confirmed that comets are time capsules from the early solar system, preserving 4.5 billion-year-old ices and dust grains that never melted into planets. Not all famous comets come back on human timescales. Short-period comets, like Halley or 67P, have orbits under about 200 years, often shaped by encounters with Jupiter's gravity. But long-period comets can take thousands or even millions of years to return. They come from the Oort cloud, a theoretical spherical swarm of icy bodies, perhaps 1 to 2 light-years from the Sun. When a passing star or the tidal tug of the Milky Way nudges one of these objects, it can fall inward on an orbit so elongated that it's practically a straight line. Comet Hale-Bopp, spectacular in 1997, won't be back for roughly 2,500 years. Some comets we've seen will never come back at all, escaping the Sun entirely. So, if you want to see a comet with your own eyes, what actually matters? 2 things: brightness and geometry. Astronomers express brightness with absolute magnitude, but for you the key question is, will it come close to both the Sun and the Earth? A small comet that swings very close to the Sun can outshine a much larger one that stays far away, because the solar energy it absorbs increases roughly with the inverse square of distance. Halving the distance quadruples the energy. To hunt comets, you need a dark sky, away from city light, and a simple star chart or app. Many bright comets are visible with binoculars, and some, like Neowise in 2020, become naked-eye objects glowing near the horizon before dawn or after sunset. The tail always points away from the Sun, so its direction in the sky is a compass needle back to the star that's heating it. In the next decades, automated telescopes like the Vera C. Rubin Observatory will scan the entire visible sky every few nights, discovering thousands of new comets and tracking their paths in exquisite detail, turning each icy visitor into another data point in the story of how our planetary system first came to be.